I'm a postdoc fellow at the McGill University, and today I'm going to talk about the flexible inductive wireless power transfer system with an onboard temperature sensor. This is the outline of my presentation. I will start it with the short introduction, and then I would describe the flexible wireless power transfer system, and then result, and finally I would finish it with the conclusion. So let's start it with the introduction. We know that the functionality of the electronic devices, all kinds of the electronic devices, is depend on the reliability of the power supply. So normally wearable systems and implantable medical devices are powered by the battery, but as a matter of fact, the batteries have a lifespan and they have to be recharged or replaced. So wireless power transfer technique can be a appealing technique for the implantable medical devices. Wireless power transfer can be done in three different methods: acoustic, radio frequency or RF, and inductive coupling. Of course, each technique has own advantages as well as drawbacks, but the inductive coupling sounds promising because of the simplicity of the implementation. Normally, if we look at the literature, we see that the inductive coupling is implemented on the conventional printed circuit board, which is commercially known as a FR4. These kind of boards are highly rigid, and then they cannot be used for the in vivo purposes. So here we are motivated to propose the flexible wireless power transfer system. Our proposed wireless power transfer system comprises two different units. The first one is the transmitter unit, and the next one is the receiver unit. In the transmitter unit, we have a Royer oscillator. This Royer oscillator it's quite simple because it doesn't need any extra or external control signal. On the receiving unit, what we have is the rectifier to convert the AC to convert the harvested voltage to the DC one, and then in order to stabilize this voltage, we have a regulator, and then this regulated voltage will be fed to the load, which is the temperature sensor. So for this system, the transmitting unit is implemented on the rigid board because it does not matter, but the receiving part is implemented on the Kapton strip as a substrate, and then we use the printing, and then the electrical connection is printed by using the conductive silver ink, and then we cure this system at the 140 degree for half an hour. So let me show you some result. Here you see the oscilloscope traces. The blue one is the signal one excite the transmitting unit, and the red one is the one that received from the flexible part. So you can see that once we rectify and regulate the voltage, we would be able to get something around the 3.3 volt. This is here at the middle, you can see our experimental setup. We try to read the output of the temperature sensor by using the oscilloscope. And here you can see for the different voltages, we got the different, for the different temperature, we got the different voltages, and there is a quite linear response for this system that should indicate that the system has a linear response. So also we testify the performance of this device in the liquid medium. So we immerse the system in the water tank, and the water tank is placed on the top of the transmitting unit. Here you can see we were able to measure the water temperature, and so that shows that this device also can be worked in the liquid medium. So let me conclude this work. So here we propose the flexible wireless power transfer system with the integrated temperature sensor. We experimentally demonstrate that by using the 5 volt input DC, we would be able to get the 3.3 volt rectified and regulated voltage at the load. And the behavior of the system is testified in the two mediums, air and water.